So now we want to generalize what we're finding for line integrals and vector fields and think about what this is really measuring for us. So you have some curve C and you're trying to move along that curve. Your vector field is pushing in a particular direction and you want to go in the tangential direction. The tangent is the direction of motion and the vector field is just the vector field in existence where your curve is. So when you find your line integral, what you're finding is a measurement of how much that vector field is pushing you in the direction of t. So in other words, it's a measure of how much your vector field is helping push you along that curve. So over here you've got a diagram and you can see you've got this curve here. Sometimes your vector field is going with you. So in that case, it's got a positive contribution. Right? So over here, your vector field and your tangent are kind of pointing in similar directions. That would have it so that it's positive. But over here, they're pushing in opposite directions, right? The tangent of the curve is over this way. It's wanting to go this direction, but the vector field is pushing this way. So that would be a negative contribution, which I'll highlight in pink right there, right? So that's a negative one. So this vector field just exists and you place the curve in that vector field. And then t has this orientation, this curve has this orientation, and the vector field can sometimes help you and sometimes hurt you. So a measurement of how much the vector field is helping is what we're looking for. And there's a fancy name for that. It's called circulation, which is denoted by an uppercase gamma. That is the symbol gamma, G-A-M-M-A. It's a Greek letter. I'll just put that in right here. Uppercase, gamma. All right, now how are we going to evaluate this integral? So what do we do? So assuming that that curve is parameterized, right, that we can do so, then we already know that t, we found that a while ago, that is the derivative of your position function divided by the magnitude of that derivative. Arc length s is the distance along the curve. We've done this before as well, right? Arc length is that distance, right? Everything from the earlier chapters is coming home to roost. Therefore, ds dt is equal to speed, which is the magnitude of your r prime. So ds would be r prime dt. Now putting this all together, this function, or excuse me, this integral of f and t, right, f dot t, would be the integral of f dot, now t is r prime over the magnitude of r prime, times ds, but ds is the magnitude of r prime dt. So here, just so you can see, this is the ds part, and this is the t part. Okay, so obviously we cancel a couple things, and then we multiply. So this would be equal to the integral of the vector field dot product with r prime dt. And we would go from A to B along our curve, right? Assuming that our curve is parameterized somehow. All right, that leads us to our formulas. So there's a two-dimensional formula for circulation and a three-dimensional formula. Okay, now both of these are circulation integrals. You can spot that they're circulation integrals because they have the t, which is the tangential vector. So this is circulation integral. And I'm going to say it in 2 dimensions, and I'm going to say it in 3 dimensions. All right, so this is the circulation integral right here. Right, once you see that, that's the circulation integral. Right, this is circulation. Okay, so how can we rewrite this? Well, we just saw what we just did on the previous page. That is also equal to the integral from A to B of that vector field dot product with r prime of t, assuming that we have some parameterized curve. So that works. That's another circulation integral. And then you can do that in 3 dimensions as well as 2 dimensions. All right, so then we can also write that as the integral from a to b of f dr. And we could say that over here, integral from a to b of f dr. That's another way to write the circulation integral. All right, well, what does that mean? Well, f dr is really the integral from a to b. Now think about what f is. F is actually f comma g, right? It's some vector. So f comma g dot product with dr, which would be dx dt, dy dt, dt. All right, so then putting that together, I would say that this is equal to the integral of a to b f dx, because I'm going to take this dot product. The dt's would cancel, so dt's would go over there. So it'll be f dx plus g dy. Right, this is another one that we use a lot. So we use the first one a lot just to note that it's circulation. We use this one right here a lot, and we use this one down here a lot. All right, same thing over here. So we would use the top one up here a lot. And obviously the first one, because the first one's how you denote that you're going to have that. And then I'm not going to do this again. It's the same work that I just did. This would be equal to the integral from a to b, and it become f dx plus g dy plus z, or h dz, sorry, h dz, because your third component of your vector field is h. So it's h dz. All right, that all seems well and good in practice, but let's see an example, or maybe two. Okay, so we're going to evaluate the circulation. Again, so once you see this, you know that this is circulation that they're asking for. And obviously I'm stressing that because there's other things that can happen. There's another one in particular we do. All right, so our vector field is negative yx, and I actually drew that for us here. So our vector field is negative yx, and we're going to look at the upper semicircle of the radius 4 centered at the origin, and I'm going to add in, it's going to be traversed counterclockwise. So let me just add that in. That's a typo. It should be there. All right, I will add that in. So that means that we're going this direction on that circle. All right, so we need to be able to parameterize this. So if we're going to do a circulation, right, in 2 dimensions, we need r of t. We need the parameterized curve. All right, so that's what we're going to work on first. So we're going to parameterize the curve. Okay, so r of t, and luckily for us, we all made it through parametric and polar functions in Calc 2, as well as learning this in Calc 3. To parameterize a semicircle, it's just the radius, which is 4, times cosine of t, and then 4 sine of t. And if we want only the upper part, oops, that should be a bracket notation right there. Sorry. Bracket. We want t to go from 0 to pi. Remember, that's always part of a parameterization, is to have a domain. And that's our domain because we want the upper semicircle. Looking ahead to the formula, we're going to need the derivative of r. So let's find that right now. R prime of t would be negative 4 sine t, 4 cosine t. Now, what about our vector field? Okay, so when we found this r of t, remember that r of t is x of t, y of t, or x of t, y of t, z of t. So that means once I have my new parameterization, that's x and that's y. And those are the x and y I would use for my function, or for my vector field. So this is now x and this is now y. So when I want my vector field was given to me as negative y comma x. Aha, but those are not going to be those values anymore. It's going to be now negative y, so negative 4 sine t and then x, which was 4 cosine t. All right, so I parameterized my curve and I rewrote my vector field in terms of my new x and y. Now we're going to put it together and actually find the integral. So the integral from a to b of, well, actually let me not write that way. There, the integral over the curve c, that's what c stands for. The integral over the curve of f dot t ds for that piece of arc is equal to the integral from 0 to pi, that's my a and my b. Oh, I should label that. This is a, this is b. That's why you have to have them when you parameterize, right? All right, and then I'm going to take f, which is now negative 4 sine, actually, one second. I just thought I'm going to write the basic formula again, just so you can see it. So what we're doing is this piece right here. We're taking the vector field and dot producting it with r prime. So our vector field is now negative 4 sine t 4 cosine t. That's now f, right? And then we're going to dot product it with our r prime, which we wrote right here. Negative 4 sine t 4 cosine t dt. Okay, so taking these two and multiplying them. Oh, and this is r prime right here. That's this piece, r prime, right there. And we're dot producting them. All right, so multiplying, negative 4 times negative 4 is positive 16. So this would be the integral from 0 to pi, right? Because that's your a and your b, right? From 0 to pi of 16 sine squared minus, oh no, plus, because it's minus, or plus times plus, sorry. 16 sine squared t plus 16 cosine squared t dt. Right, but sine squared plus cosine squared of the same angle is 1, right? That's the Pythagorean identity. So this is the integral from 0 to pi of 16, which of course would be 16t from 0 to pi, which is going to become 16 pi. Now I'm adding in a part B. Let's take the same vector field and let's compare what happens when we're looking at y equals the square root of x. And we'll be able to look at these. Okay, so I've already drawn it right here. Y equals the square root of x from 0, 0 to 4, 2. Looks like that. Okay, so we need to parameterize this. So we're going to parameterize our curve. Okay, r of t. The easiest way to parameterize is to take your curve and to make it so that t is your x, and therefore the square root of t would be your y. And we're going from 0 to 4, right? Because if x is your t value, right, then this is x is 0, this is x is 4. So these are now your t values. Now remember, when you did this, this is now x and this is now y. All right, so now let's come up with r prime. So this would be the derivative of t is 1. This is really t to the half, so that would be 1/2 t to the negative 1/2. Or if you like, it's 1 over 2 square root of t, like that. Now our new vector fields, we need to rewrite our vector field. So the vector field was negative yx, but now we're going to rewrite it with our new y and x. So it's going to become negative square root of t, right, because that's y, and then x, which was t. All right, now let's find the integral. So the circulation integral over the curve of f dot t ds over the arc, right, the arc of the curve, is equal to the integral from a to b of f dot product with the derivative of my parameterization function dt. let's see, which is equal to the integral from 0 to 4. F is now negative square root of t, and r prime is 1 over 2 square root of t dt. Okay, multiplying. This is the integral from 0 to 4. That's negative the square root of t plus, this is t over 2 square root of t, or t over t to the half, if you will. That might make it easier to see what you have to do in a second. All right, so this, just using a little bit of algebra, this is really t to the 1, this is t to the half, so you subtract the powers. So I know I need to integrate this in a second, so I'm going to rewrite this as powers, because powers are way more useful for integrating. Hey, wait a second. These are the same. This is a t to the half, and if you take t to the 1 over t to the half, that makes t to the half as well. So this is negative 1 t to the half plus 1 half t to the half. So this is really the integral from 0 to 4 of negative 1 half t to the 1 half. Which, integrating that, I mean, you could use maple too, but this would be t to the 3 halves times 2 thirds. And then we're taking that from 0 to 4. And so that's 8, right? 4 to the 3 halves is square root of 4. Oh, sorry, that's a 2 there. Square root of 4 to the third. So that's 2 to the third, which is 8. Oh, 1 second. There we go. My 3 halves got all messed up. So this is negative 1/3 times 8, which is negative 8 thirds. Now, what in the world is going on? Why was this one negative and the other one's positive? Now for that, that's why I have the picture. So when you look at the picture for the previous one, the vector field is pointing in the direction of the curve. You see how the little arrows are pointing in the direction of the curve? So our circulation is a really big number. It's 16 pi because the curve, the field is pushing along the curve. So field is 16 pi, which is huge because the field, the vector field, is doing a lot of pushing in same direction, right, as the curve. That maybe wasn't the smartest place to write that, but that's what I did. So your circulation is a very large number because these arrows are pointing right along that curve. Okay, but when I look at this one, that same vector field, but look, they're not pointing. I'm trying to go this way along the curve, and all the arrows are pointing against me, right? So the circulation is negative because the vector field is pushing against the curve. It's not helping it, it's hindering it. It's like this, the vector field is the flow of the water, and you're trying to swim against that current. Those arrows are the current, and you're trying to swim this way, right? And the arrows are not helping you. The current is not helping at all, right? That's what's happening on. That's why that's a negative number, right? Right. Hopefully that helps with understanding what circulation is. Right, circulation is the amount that the vector field pushes you along your curve. If it's a positive number, it's pushing with the curve. If it's negative, it's pushing against the curve.